My name is Rachel, head of the alumni program, and with me I also have my amazing team, Elena and Dante, who's just joined the team. And so today we have our News from the Lab series, and today we're going to be focusing on um, the next frontier in neutrino detection. So it gives me great pleasure to introduce today's moderator, and I have to make sure that I pronounce this right. It's Adelina Lintuautu. I hope
Very good.
is that okay? Good, thank you. So Adelina is an applied physicist and science communicator based at CERN. She completed her PhD in experimental particle physics at the Karlsruhe Institute of Technology, where her research focused on trigger level analysis at the CMS experiment. And she now holds a position in science education at CERN, bridging her background in experimental physics with her passion for public engagement. Alongside this role, she remains active in research, both in the field of informal education and through her work with HEP research group in human well-being. I'd like to find out
That's
more
right.
about that. We're not here today for that. So Adelina, thank you so much for agreeing to be our moderator today. I'd like to hand over to you now, please.
Thank you very much, Rachel. It's a pleasure to be here. Now it's my turn to introduce our two speakers. First up, it's Pierre Granger, research fellow at CERN and co-convener of the DUNE Atmospheric and Exotics Physics Working Group. His experience spans from detector operations as proto-DUNE to the development of official DUNE analysis frameworks. And with him is joining Adrien Blanchet, who is based at Sorbonne University in Paris, and he's a research fellow at CNRS. He is involved with analysis of neutrino oscillations at T2K and is also contributing towards upcoming future CP violation measurements at Hyper-Kamiokande. Now, thank you very much for both of you presenting here today, and the floor is yours. You may present your slides.
Thank you very much, Adelina. We're going to share our slides. There you go. And thank you very much also for the invitation, Rachel, for the alumni group, for us the opportunity to actually share the work of the neutrino group at CERN. So let me introduce first the neutrino as a CERN perspective, let's say. So I choose a path in which would interest people from the LHE, let's say, that would be interested into like neutrino physics. Why should we care about neutrino physics? What CERN should care? So basically, I started like this. So basically, we have the standard model that is the standard model that we use nowadays to describe the interaction of the particles that we know. And basically, the standard model is not just a collection of particles and interactions. It's built against gauge symmetries. And essentially, these symmetries that we know today, the real ones, will introduce some false carriers, some false bosons, essentially, that will provide some allowed interaction and provide a structure to the particle that we know today. So CERN turned this symmetry picture into experimental reality. And here are three picked up key experimental program milestones by CERN. So the first one I've chosen here is the one of Gargamel in 73, in which was essentially a bubble chamber. We were taking pictures, like a photographic picture of the tracks in the detector. And here you have a beautiful picture of the neutrino interacting with the nuclei without an outgoing lepton, which means that there was a neutral boson creating these interactions here. And at the time, the Z boson was not discovered. And that's why it was actually predicted by these new symmetries. And 10 years after that, the UA1 and UA2 experiments discovered the two bosons, the W boson and the Z boson. And as you can see, by colliding protons with the antiproton, you create a Z boson that will basically create two jets of like back-to-back positron and electron tracks, let's say. But the interesting fact about this collision is that if you make a work of like kinematics, you end up with a mass of the Z boson that is non-zero. And the gauge symmetries, all the bosons are massless. So there was a breaking of symmetry somewhere. And the theoretical answer was formulated by both Engler and Higgs. And we had to wait a few more years to actually discover the Higgs boson with ATLAS and CMS with two different channels. I've put here the beautiful plot of Atlas in here. And here the invariance mass has been found to be 125 GeVs. So the particle associated with the mass giving mechanism has been also finally and validated this symmetry, essentially. But the standard model is pretty consistent now, we know, but yet incomplete. So for example, there is this question of why there are only 3 generations of particles, although those particles have been like found only by chance, let's say. Why those masses? This is just empirical. The standard model doesn't provide any explanation what the mass are those ones. And finally, as you can see, there is those outlier here that has the mass of the neutrino, which is very surprising actually in the standard model, because the standard model, I think, are thinking the neutrino as massless. And the reason for that is that we know that the neutrino are only left-handed. So the Higgs coupling can't actually explain the mass of the neutrinos. And we know that neutrinos have mass because we have discovered the neutrino oscillation. So what is flavor oscillation? So flavor oscillation essentially is the result of quantum interferences between the flavor states. So basically, if we create a particle, it is created as a given flavor. But if the mass and the flavor state don't match, the particles are produced as a superimposition of my state. And because those mass states have different masses, they will propagate at different speeds, a different wave packet, speed of wave packet. And the phase that I wrote here is dependent on the mass of this wave packet and the distance that it travels and the energy of the particle. So you can see that you produce a neutrino nu-mu, for example, and it will propagate as a superimposition of nu1, nu2, and nu3. And finally, when you want to detect the neutrino, then you use the weak interaction, and then you propagate, you project back to the flavor basis. And this phase difference will create some interferences that leads to a disappearance of the original flavor that you have been emitted. And those neutrinos have not disappeared. They are also appeared in another flavor, but usually you just like see the muons, let's say. So the neutrino oscillations are parameterized with the PMNS mixing matrix. That's how we describe those oscillations. So essentially, it will link the flavor components with the mass component with this mixing matrix here. And the mixing matrix is parameterized by mixing angle that will actually describe the amplitude of the oscillations. And with quantum physics, we have the phase difference that are playing a role here. And you can see that this is actually dependent on the ratio of the distance and the energy of the neutrino. So in total, we have 4 measurable free parameters for the PMNS description of these oscillations. So we have 3 mixing angles plus a CP complex phases that Pierre will also introduce a bit later. And we have 2 also independent mass differences, let's say. So this, of course, the standard model didn't say anything, and we had to measure it. So for more than 20 nowadays, we know almost all the values of those parameters. And this is not by chance. This is really because it validated the PMNS framework, because we've been measuring all those parameters with different sources of neutrinos and different technology of detection. So here, for example, you have the first plot on the left, the L over E dependency with atmospheric neutrino with Super-Kamiokande. On the center, you have like reactor antineutrino with another technology, which is the Camelon project. And finally, you have the Chinese project Diabe, which was looking at different baselines, so different distances of propagation for the neutrinos. And still, we were different, sensitive to different parts of these PMNS matrix parameters. All right, so the question now is why studying neutrino is interesting. And one of the reasons could be because of the tiny masses of the neutrinos. And I'd like to quote the Murayama quote here, which was the chief founder of the IPMU Institute in Tokyo, which was saying that neutrino interference, which is neutrino oscillation, is a unique tool to study physics at very high energy, already probing up to lambda equals like 10 to the 40 GeV. So as a matter of comparison, like CERN is like 10 to the 3 GeV for the moment. So this is clearly some out of reach that humanity could reach with proton colliders. So this is very interesting actually to look at those interferometers. And the hope with those study of neutrino oscillation is to do precision measurement of those parameters that could reveal some flavor structure of the particle that we can't actually reach for the moment. And FCC in the future could help us see if this new symmetry that we may found could have an origin in high energy physics. So that's why I would say that CERN is involved, and we are actually contributing to the DUNE and Hyper-Kamiokande detector. So now Pierre is going to talk to you about the current status of these oscillations.
Yes, so as Adrien explained, we have all these parameters in the PMS matrix that are measured by different experiments. And you can see really on this plot here, the evolution of the resolution on these various parameters that we had with time. And you can see that for most of these parameters, we really managed with time and with many experiments involved, as you can see, and as it was described, we really managed to measure them in a very precise way. However, you can see that there are some outliers in this framework. You can see that our knowledge of the delta CP phase, that is the phase that drives CP variation in the lepton sector, is still very poorly constrained. You can also see that our knowledge of the current mass ordering, that's to say which mass state is the heaviest, is also for now unknown. And we also have some additional uncertainty that lies in the actual octant of theta to 3, that is this mixing angle, because you can see that the sine square of this angle is very close to 45 degrees, and we don't know in which specific octant it lies. So these measurements are the main challenges of the future experiments. And also an additional challenge is to verify the validity of the whole PMNS paradigm and to know if there is some physics even beyond that, or if that framework is really able to express all what happens in neutrino oscillations. So typically with these very precise measurements, we want to answer a lot of fundamental questions because being able to very precisely measure all these mixings and mass states might allow us to know a bit better what is the origin of neutrino mixing, to know if there is some underlying flavor symmetry, because you can see that in the quark sector, you have a similar matrix that drives the mixing, that is the CKM matrix. And you can see that this matrix really allows for very small mixing between the different quarks. While in the lepton sector, we have this matrix that is way more even with much larger mixing, and that might hint to some specific symmetries that we still have to discover. Also, there are still the mystery, as Adrien mentioned, to know what is the process that gives neutrinos their mass, and to know if the whole standard model that we have for neutrinos is really complete. And for all of this, we really need to have next generation experiments that are able to measure all the PMNS parameters with great precision, as well as being able to measure effects that are possibly beyond this model. So another thing is that all these theoretical questions are very linked to astrophysics and cosmology, and we can really use neutrinos as probe for the universe, because we can do some very high energy physics with very high energy neutrinos that can come from astrophysical sources. Some neutrinos with more than tens of TeV have been detected, for example, in the sea. We can also make some link with the supernova core collapse that emits some neutrinos that we can detect to better understand the process of these collapses, as well as understanding, for example, the asymmetry between the matter and antimatter, for which CP variation in the lepton sector is mandatory with the current models that we have. So in order to do all of this, the key kind of experiment that we are currently using are these long baseline neutrino oscillations that are made with accelerators. So the way we produce neutrinos is by actually using accelerators that are able to collide protons on a fixed target, often graphite. So you have a proton that arrive, they are sent to a target, you produce a lot of charged mesons that you are then able to focus with some specific magnetic horns to only keep the negative or the positive mesons, and then you let these mesons decay in some decay tunnel where they can produce many nu mu or nu mu bar, depending on the sign that you select. And this allows you to create like a neutrino or anti-neutrino beam that you can then let oscillate on large distances. You can select rather easily your energy as well as your distance, because you choose your source and you can just put a detector at a specific distance from that source. And this really allows you to kind of tune L and E to be able to probe some specific L over E values that are really driving the oscillations. And typically what you do is that you have these nu mu and nu mu bar that you can then study the disappearance of at the far detector, or the appearance of nu E and nu E bar with the process that Adrien described. And now Adrien is going to present the experiment that is really the leading one currently on this topic, and that is T2K.
Right, yeah. As you said, this is one of the world leading experiment in the field for the moment, waiting for the next generation of experiments. So the CERN group had a lot of implication to this project, especially the upgrade of the near detector that we just introduced in a few slides. So first of all, as Pierre said, we use muon beam of neutrino that is created in Japan by the facility called J-Park here. And we let those neutrinos propagate into a given direction, and we shoot essentially the beam towards Hyper-Kamiokande. And at these distances, which is 295 kilometers away from the source, we expect most of the neutrinos to have oscillated. Actually, most of the neutrinos oscillated to neutos here that we can't detect for some reason. But some of them are left to nu mus, and we can also detect the appearance of a new flavor of neutrino, nu E's in that case. But of course, to measure with precision those parameters, we also want to measure the interaction of neutrinos before they oscillate. That's why you use a dedicated near detector that I'm going to introduce a bit later. So yeah, essentially, as I said, we are looking for the oscillation probability to be maximized. And this oscillation probability is maximized for 300 kilometers away from the source at 600 MeV of energy of the neutrinos. So to get that energy and to maximize the flux on that energy specifically, we are actually shooting the beam a little bit off axis. So basically the beam center is not pointed directly towards Hyper-Kamiokande, but it's a little bit off axis. And because of that, we end up with a peak, the flux of the neutrino that is much more narrow around the 600 MeV target that we wanted to measure. And the good thing about it is that we don't actually measure directly the energy of the neutrino. We actually measure the energy of the outgoing lepton. We only see the muon or the electron associated to the neutrino directions. But because we know the energy of the lepton and the energy of, the angle between the beam line and scattering angle of the lepton, we can infer on the neutrino energy. And thankfully, at this energy, we are also dominated by this process, which is called the charge current quasi-elastic, in which we know very well the distribution between the association between the energy of the lepton and the energy of the neutrino in that case. So this essentially helps us to measure very precisely the disappearance of those neutrinos without too much smearing, I would say. So this is very important because, yeah, in the far detector, we only see the lepton coming out. We don't see the protein, the hadronic part, for example. And Hyper-Kamiokande is essentially this water tank that is located inside the Kamiokande mountain in Japan. And what we can say about it is that we detect the electron or the muons with water Cherenkov effect, essentially. And the idea here is that we have a good particle identification. So we can really separate well the two contributions between muon and electron, because you can see that the electron is actually showering when it interacts into the water, which create those fuzzy rings that we can detect inside the detector. Where the muons, on the other hand, is producing very sharp rings. So we can very separate the two and infer on the nature of the neutrino that have oscillated or not. And also we can do some energy reconstruction very well, because we can just count the photons here to actually reconstruct the energy of the lepton in here. But unfortunately, Hyper-Kamiokande has its limitation as well. And the limitation that is the most important for us is that it's not magnetized. So we have some background that we need to control. And that's why we use the near detector, which we call ND20, because it's placed at 280 meters away from the target, let's say. And it consists actually of two targets of neutrino that are placed around time position chambers that can detect the particle and measure the momentum. And this ND280 detector is actually magnetized because it's located inside the UA1 magnet. So the experiment was at CERN that we just talked about for the discovery of the Z and W boson, actually. And yeah, I just want to emphasize the fact that this detector is absolutely essential to reduce the systematic uncertainty and the neutrino flux and the cross-section, before measuring the oscillation parameters. So that's why we actually, to do precision fitting, wanted to upgrade the new detector. So essentially, one of the main limitations of the detector we had here was the fact that those targets here are actually vertical. So basically, if you have a muon or an electron that is actually produced perpendicularly to the beamline, we are not able to reconstruct it because we don't have any time projection chamber in between to catch them. So essentially, when we go like perpendicular, we don't have any efficiency to detect those neutrinos. This is a problem because Hyper-Kamiokande sees it, and we only rely on a model to describe actually those scattering angles in that case. So yeah, also we don't have much sensitivity into reconstructing the hadronic part, essentially the protons. And for the moment, with the current detector, we don't have any measurement at all on the neutron parts because of the technology we used. So that's why we chose to actually upgrade the upstream part of the detector with 3 new detectors. So the first one is the Parity, which is the new target of neutrino, that is placed around 2 time projection chambers, which we call the high angle TPC, to detect the lepton with high angle. And finally, all of the 6 faces of the cube is covered by what we call the time of flight detector to essentially reject background. And the CERN has been involved into this development of the upgrade and the commissioning as well. And it has been approved by the SPSV in 2019, and it ended up with the NP07 creation for the development of those new detectors before shipping them to Japan. And I'm going to spend a little time discussing about those detectors, essentially. So as I said, the SFGD is the new target of neutrinos. So it's composed of little cubes of carbon, essentially, CH, if you want to be precise. The neutrons interact and they produce light, actually, inside those cubes. And the light that is produced in those cubes is propagated into these wavelength shifter fibers, actually, and we detect the light with silicon PMs at the end of it. So in the end, it adds 2 tons of fiducial mass for the neutrino to be detected, and we are able to reconstruct the lepton, as you can see here on this sketch, but also the hadronic part, where we have 2 protons actually in this simulation here. So such a detector would be super useful for us for constraining our model and improving the models to measure the oscillation in the end. So the CERN for this detector has been in charge of the mechanical box that all the things together, because this is 2 tons of mass that we need to hold. And we've been responsible for the mechanical box assembly. And also, as you can see, there are some concrete blocks here to monitor the deformation of the box here. So essentially, that was the contribution of the SFGD by CERN. And now I'm shifting to the high angle TPC in that case. So the high angle TPC are those 2 blocks of detectors that are used now to identify the particle and reconstruct the momentum through the curvature of the particles that are crossing them. And this is essentially some gaseous argon TPC that we use here. It's composed of 4 field cages that has been produced here at CERN with 32 resistive micromegas, which are these detector technologies. And yeah, this was the first time this technology has been used in a large-scale experiment as T2K. So we have first used a prototype at the SPS beam dump to test if the technology was viable. Then we produced the first field cage and installed the detectors in front of on the anode, actually. And finally, we tested the first field cage in the T9 area with real particles to see if it responded well. And finally, we ended up like producing on the large case the 4 field cages that was needed for the experiments to run. So all of this was conducted at CERN, and the group has a very important implication into those developments. And finally, I want to talk about the TOF, in which the CERN also contributed as well. So essentially, as I said, the CERN is just the TOF is just made of 6 planes covering 4 pi of the particles that would cross. So essentially, that helps us distinguishing the particle that are crossing the detector because they are backgrounds, and they can also reject the particle that are entering the detector and their life into the target. So we don't think they are neutrino-based because when they are actually not. So that is actually super useful. And we have been developing those plan in NPO7, and you can see us actually installing the detector at JPark at the very end. So yeah, in the end, we install everything into the pit where the ND280 detector are actually placed. So first of all, you can see the shipping of the HATPC, then we have also the SMPD, and finally we have the TOMF plane that we actually covered the thing and closed up everything. And now we are taking data, and as you can see, we are still, we are taking data now with beam simply. And yeah, finally we are ongoing on the data analysis. So we've been taking data since May 2024. And yeah, we have been developing the reconstruction in the past year. So this is quite challenging because we have to match the tracks between different technology of detectors. It takes some time, obviously. And we tested for the moment with control samples of neutrinos that interact essentially outside of the detector. And the milestone that we have been able to achieve is essentially that now the detector are well understood in simulator and ready for physics, I would say. So unfortunately, I can tell you much more than that because the first results are going to be presented next month at the Neutrino conference. So yeah, this is actually nice because we are ready for the next upgrades. And by next upgrade, I mean next upgrade of the far detector. So now the far detector will not be Super-Kamiokande anymore, but Hyper-Kamiokande, which is the next generation. So essentially, this is the same technology, but it's 8 times bigger than Super-Kamiokande. And because we are also upgrading the beam, the power of the beam in here, we end up with like 20 more like neutrino at the same time. So essentially 6 months of data taking of Hyper-Kamiokande will be equivalent to take as much neutrino as the whole data taken by the period of attributed to T2K. So this will be precision physics very quickly. And finally, I just want to say that in that case, the beam upgrade is on its way because we are reaching 1 megawatt. All right, thank you. And yeah, so now for the next year will be some fine tuning of the beam, and we're gonna probably reach the nominal power for the Hyper-Kamiokande array. So speaking of the far detector, the cavern has been fully digged, and now we are actually installing the detection panel before filling up the place. And we are expecting to take data in 2028. And finally, I just want to briefly mention the contribution of CERN for the Hyper-Kamiokande detector. So the first one is the water Cherenkov test experiment, which is testing those new multifold to multiplier technology that will be installed into the far detector. And so it's been tested last year in the T9 beamline. And also the CERN is also providing dedicated space for the test of the electronics that will go underwater in Hyper-Kamiokande with the Neutrino platform 08 facility that we are providing. All right, you have a few pictures in here to see what's happening in there. So now you're going to speak about the main contribution on DUNE, actually.
Yes, so a complementary experiment to Hyper-K that is also a next generation experiment that is currently being built is DUNE, that stands for Deep Underground Neutrino Experiment, and that is a long baseline neutrino oscillation experiment that will be located in the US. So as you can see, this experiment will feature like very similar elements as, of course, T2K or HK. It's again a long baseline neutrino oscillation experiment. So first we have a neutrino beam that will be created at Fermilab, that is located near Chicago. This beam will be the most intense neutrino beam in the world after full upgrade, and the strategy chosen for DUNE is different than from T2K and Hyper-K. Here, that's a wideband beam that really spans several that spans a large band of neutrino energies in order to be able to cover two different oscillation peaks. Then we'll have a near detector facility where we can measure the unoscillated flux and monitor this flux and have some reference and measure precisely the cross-section of neutrinos with argon, that is the detecting material that we use for DUNE. And then we have a much longer baseline than the Japanese experiment with 1,300 kilometers of baseline that the neutrinos are left to oscillate for, before being detected in some massive far detectors that are liquid argon time projection chambers and that measure the oscillated fluxes of neutrinos to see new appearance and new disappearance. So DUNE collaboration is very large. As you can see here on this picture that was taken at CERN for some collaboration meeting. And this international collaboration is composed of more than 1,500 collaborators across more than 200 institutions. And you can see that we have collaborators from all over the world, from 40 countries, including CERN in the list of countries. So DUNE is going to happen in two different phases. There will be a phase one initially with two far detector modules, as well as an initial beam of only 1.2 megawatt that can be later upgraded. And these two modules will be liquid argon time projection chambers of 17 kiloton of liquid argon each. The near detector will be made of three different detectors, including a LRTPC and a muon spectrometer. Then there is already a plan for a phase two of DUNE, where we will add two additional modules in order to have a total of 4 modules, as well as an upgrade of the beamline to a power larger than 2 megawatts, as well as also a more capable near detector that will include a high pressure gaseous argon TPC that will allow us to better constrain the cross-section of neutrinos on argon. So let's look a bit at all the various elements. So first we have this beamline from LBNF that is produced with 120 GeV proton beam that is sent to a target to produce the mesons and so on, as I explained earlier. And the flux of DUNE will be quite wide and produce energies from produce neutrinos with energies from around like 500 MeV up to like 6 to 8 GeV, so with a very long tail. And this will allow to cover two different oscillation peaks and to very precisely measure the oscillation parameters. Additionally, this high energy tail allows to detect neutral charge current interactions because the energy threshold to be able to produce tau leptons is around 4 GeV. So having flux above this really allows to detect these neutrinos and to probe the free flavor oscillations and to really check in depth the PMNS framework. So you can see here some pictures of here the location at Fermilab where the beam will be located, and then you can see a part of the accelerators also. So then another key element is the use of liquid argon time projection chambers. So given that we have these relatively high energy flux of neutrinos compared to T2K, we have a peak was around 600 MeV. Here in DUNE, we have a peak of energy for the neutrinos that is around 2 to 3 GeV. So this means that we have a quite heavy hadronic system that we need to detect to be able to correctly reconstruct the energy of the neutrinos. And in order to do this, we use the LRTPC technology, that is time projection chambers, in which the charged particles ionize the medium and produce both some light that is detected, as well as some drifting electrons that are then collected on different readout planes, and that really allow to make these wonderful images of the interactions with some millimetric resolution. And you can see that this allows to perfectly see the interactions and detect the hadronic system and make some very precise measurement of the energy of those neutrinos. In addition, liquid argon really provides a low kinetic energy threshold. So this means that we can detect low energy protons, which is impossible in water Cherenkov detectors, for example. And we also have some dedicated photon detection system to be able to collect the light that is emitted in the detector. So another and last element is the DUNE near detector that is really mandatory to be able to really monitor the initial flux before oscillation, as well as measure the cross-section of interaction of the neutrinos on argon. And in order to do this, DUNE will have three different systems. The first one is called SUND, and it's a tracker that will stay on axis of the beam. And then we'll have two other detectors that will be able to move together at different off-axis positions. That is called the PRISM framework. And these detectors are a liquid argon detector that will be the main near detector that uses the same technology as the far detector, except for its readout that here is pixelated in order to be able to cope with the higher rates that we'll have at the near detector, as well as a muon spectrometer that allows to measure the sign of the exciting leptons and to tag neutrinos from antineutrinos. So now I will tell a bit more about that PRISM technique. So in order to be able to really benefit from these wide range energies, we need to be able to really know what is our flux at different energies. And in order to do this, a good solution is to move at different off-axis positions, because as Adrien explained, when you move off-axis, for some kinematics reason, you totally shift your energy flux, and it also becomes more peaked. So this means that if you measure your flux and interactions at the detector at different positions, you can actually probe different energies and scan them and be able to better constrain your flux and cross-section systematics in your analysis. So you can do this either in a let's say, naive way, where you would take all these measurements and try to combine them statistically. Or another option that is currently being studied for DUNE is to actually try to make a linear combination of these different measurements at different energies at the near detector to be able to match the oscillated flux at far detector and automatically being able to extrapolate near detector observations to far detector without relying so much on the interaction model predictions. So now let's see how DUNE is actually sensitive to the different oscillation parameters. So typically the kind of plots we often look at for this kind of experiment is to look at the new E appearance channel, and we look for a given exposure how many new E we are expecting to detect at the far detector for the neutrino mode versus how many new E bar in the anti-neutrino mode we are going to detect. And typically, depending on the mass ordering, you have two different ellipses that span different phase spaces here in that plot. And as you go along this ellipse, you go through different true values of delta Cp. And these points are all the points allowed by theory, and then you make a measurement, and depending on that measurement, you can make a claim on the ordering as well as a claim on delta Cp. So you can see that for low energies, we have these ellipses that are rather close in the case of DUNE, so it's hard to make a big statement on the mass ordering because you have some degeneracy. But you can see that these ellipses are rather open, so you are able to tell apart the different values of delta Cp. Then, given that DUNE has a wide band beam, you are able to scan at different energies. So then when you look at energies that are between 2 to 3.5 GeV, so that is around the peak of probability, you see that the ellipses are totally flat, so you don't have any more sensitivity to delta Cp. However, the two ellipses are really far apart, and you can really make a claim on the mass ordering. And then when you go to even higher energies, the ellipses get closer to each other, so you have lower mass ordering. And on the contrary, you have high delta Cp sensitivity because they really round up. So one of the great strengths of DUNE is to be able to make these different measurements at different energies and to actually measure oscillation parameters for different values of L over E. And with these techniques, you can, in theory, break degeneracies between delta Cp and the mass ordering. And in addition, you can also check if the free flavor PMLS picture is correct, because the data that you have should always prefer the same point in every energy bin. And that's a good way to really try to search for possible new physics, because any new physics would distort the observation as function of L over E. And that's really some unique sensitivity that DUNE has. So beyond beam physics, DUNE can also do some other things. We can look at atmospheric neutrinos. That will actually be DUNE's first data, because we are going to have some far detector installed before having some beam available. And to be rather quick, these atmospheric neutrinos are produced in the atmosphere, and then they travel through the Earth before being detected to our detector. And depending on the angle they have, they will have traveled a different distance through the Earth. So this means that you can probe different baselines. That is here illustrated by the cosine of the zenith angle in that plot. That is a proxy for the baseline. As well as different energies, because these neutrinos are produced with very wide energy flux. And by looking at these 2D plots, so by looking at the rates that you obtain for different angles and different energies, you are able to be sensitive to oscillation parameters. So you can be sensitive to delta Cp at low energies and to the mass ordering at higher energies. And DUNE is actually really good at detecting these atmospheric neutrinos, and moreover good at being able to reconstruct their direction, given that it's able to fully reconstruct the hadronic system. And using these atmospheric neutrinos and combining their measurement with the beam neutrinos can really help making some richer statement on the PMNS framework, and to also gain some sensitivity to delta Cp and the mass ordering. Then some other interesting physics that can be done is about supernovae physics, as I mentioned at the beginning of the talk. So DUNE can be really good at detecting supernovae neutrinos, and to point to where these neutrinos were originating from, to be able to point towards the supernovae. And one specific characteristic of DUNE is that using argon makes it able to actually measure the new E's that allow to possibly differentiate between different supernovae models that can be of high interest for astrophysicists. So you might wonder, why am I talking about DUNE and so on, and how is CERN involved? So CERN is very heavily involved in DUNE, and it has been mainly through the installation and operation of the proto-DUNE detectors at CERN through 4 different runs that happen in 2 different phases. So there was a first phase before 2020 with proto-DUNE single phase and proto-DUNE dual phase that you can see here, that are located at the Neutrino platform. So we have 2 different cryostats in which we operate these detectors. And the second phase where we have the so-called proto-DUNE HD and proto-DUNE VD detectors that I'm going to present a bit after. So the first phase was really a great success. It showed that the liquid argon TPC technology that will be used in DUNE is really successful, and we are able to really have these wonderful images that are able to very precisely reconstruct the interactions. Here we have some beam particles that we can see have some hadronic interactions, and we can clearly see like all the children particles, and clearly measure the energy of all of them and reconstruct the interaction nicely. It also allowed us to see that the dual phase technology that was initially proposed was a bit too challenging and led to some issues. And this led to the creation of a new design, that is the vertical drift, that has been then tested in a second phase. And several publications were made, and there are also some ongoing analyses. There are even some specific physics results that I'm going to go very quickly through, some specific cross sections of protons, pions, and kaons on argon were measured for the first time at some specific energies. Thanks to proto-DUNE data, you can see here all these plots and all these publications. And measuring these cross sections can be of use for then the neutrino interaction generator models, as well as for the future DUNE physics that we are going to do later. Then there is a second phase with 2 other prototypes, so proto-DUNE HD, that is extremely similar to the single phase technology, but that has been renamed to HD, and that has been operated in 2024. And typically that's the final technical solution that is going to be used for the far detector HD version in DUNE. And you can see here the actual readout that is made with these APAs that are anode plane assemblies that are these assemblies of 3 different wire planes that are interleaved in such a way to be able to correctly have a 3D reconstruction from the readout of 3 2D planes. So you have angles of around 40 degrees for 2 views and an additional view that is at 90 degrees. And it's called horizontal drift, of course, because you drift the electrons horizontally. So this run was a success with tons of data that were acquired, and it was also able to demonstrate that we are able to really have extremely good argon purity, which is really important for all our detectors, because this means that we can drift the charges over very long distances with very low attenuation. And we even detected some very first neutrino candidates in these liquid argon detectors. And this was possible due to the fact that the protodunes are on axis of the SPS beam, way after some beam dump, so they can parasitically benefit from a beam of neutrinos that are quite high energy neutrinos, I think above 20 GeV mostly. But we can see these neutrino candidates where we can see here a new E with this huge electron shower, and here a new mu where you have this whole hadronic system and the muon going through. Then another prototype in the phase 2 that was tested is protein VD. So VD stands for vertical drift. It has been operated from 2024 to still those days, actually. And in this case, we drift the electrons vertically. And in addition, the readout is made of these perforated PCBs instead of these interleaved wires. And you can see here the full schematic of the detector. So these runs were also a success, also showing a very great liquid argon purity, very good high voltage stability, and another good performance of all the subsystems. Once again, a lot of data has been acquired with some charged beam, and operations are actually still continuing with some more calibration sources, especially on the light detection side. And finally, a final point in which CERN is involved is this full-scale VD installation mock-up that is being made in building 185. So they are really trying to get a full-scale mock-up to really try to rehearse all the installation activities that will happen in the US in the coming years. And the point here is that you are able to have the full height to make sure that all the procedures that are happening at 13 meters of height are really totally suited, and that everything will work fine. And that's really some important activities CERN is involved in. Then for the future, CERN is also participating in trying to prepare the future for DUNE and for phase 2. There are, as you can see here, many different technology choices that are proposed in order to improve the detection that we make. Some of this prototyping actually happens at CERN, but some is also made in many other labs. And the key point here is that there was a proposal addendum that was made to the initial protodune submission at SPSC to ask for a protodune 3 run, where we would have this kind of like chimera protodune detector that is made of different technologies to test different charge and light readouts all together by reusing the NP02 clearstat and by, in theory, trying to run in 2028, 2029, in order to be able to really study these future technologies for DUNE. So to tell a bit more about what is the current status of DUNE, the far detector is made of these large caverns, and the acceleration was finished 2 years ago. And this excavation work was actually nominated as a project of the year by the Underground Construction Association in the US. And finally, to show a timeline of DUNE, so the far site excavation is complete, as I've been showing, and now the whole building and site infrastructure is ongoing. And we expect to have all the future steps to happen quite soon to be able to start physics by the end of 2029 with solar, atmospheric, and astrophysical neutrinos, and to be able to start beam physics by 2031 once the beam will come on. And now I'm going to...
I just have 2 slides to introduce the next step, because yeah, what Pierre, you introduced very well is the fact that essentially we are measuring neutrino energy through the outgoing leptons, so the muons or the electrons. So essentially what we are doing is trying to improve our models as much as we can. And it would be nice if we could also directly measure the energy of the neutrino. And one way to do that would be to directly measure the decay product of the pion. So typically the neutrino are produced in this matter. So we have a neutrino here that has been produced by the decay of a pion, and this decay will produce a muon and a neutrino. So if we are able to instrument the decay tunnel with showing measuring the pion energy and measuring the muon energy, then we are able to infer directly on the neutrino energy without having all the complex things that happen inside the nuclei that we are trying to correlate with the contribution that we see from the leptonic part, essentially. So the technique is called tag neutrino beam. And actually that has been demonstrated here at CERN with the NA62 experiment that is essentially made to look at rare decay of decays, essentially. But it has been used as well to prove that neutrino tagging was possible. And they have found essentially one neutrino with a very controlled background. And you can see that the energy resolution on the neutrino energy is very impressive, like 0.34%. Is like almost probably 10%, 15% in our neutrino detector alone, if we just consider DUNE or Hyper-Kamiokande, for example. So it would be extremely useful for us. So essentially now the group is also shifting toward the NuScope project, in which we want to instrument a beamline. So basically we take the SPS beam and we use a slow extraction to reduce the flux of ions and counts. And we are measuring into the detailed volume the muons that are contributing here. And finally, we have a neutrino detector at the end to actually correlate with the neutrino interaction afterwards. So that would be the program that is very rich. So we could study the neutrino interactions, do nuclear physics, and also do some standard physics. All right, so that's the summary. I'll try to be as quick as possible on that. So CERN has a huge contribution on T2K, huge contribution on the DUNE project, the American one, and finally looking at the future with a NuScope project. Right, thank you very much.
Thank you very much, Adrian and Pierre, for the fantastic overview. Without further ado, we're going to open the floor for questions. If you have a question, you can raise your hand, or if you prefer, you can write them in the comments. And I can see that we already have a few in the comments. So I'll just start with the first one from Adam. Is the solar neutrinos deficit well explained?
Sorry, what was the question?
Sorry, let me repeat it. Is the solar neutrinos deficit well explained?
Yeah, I can answer if you. So yeah, the solar neutrino was quite a great question, actually. It was at the origin of the discovery of the oscillation of neutrino. So at the beginning, the first signal toward the oscillation of neutrino was actually just seeing a deficit of solar neutrino. So basically, we just saw less neutrino, at least I think 1/3 of neutrino that was predicted by the model that we had. So everybody was thinking that was the model that was wrong, but actually that was due to the oscillations. So now if we introduce the oscillation, the matter affects how the neutrino evolve into the sun and exit the sun, then we can understand the flux that we measure on Earth, actually. So it's actually quite well understood and actually part of the proof that neutrinos are oscillating now.
Thank you. I hope that answers your question, Adam. Before we continue with the questions in the comments, perhaps we can give it over to Trivan, who has raised his hand. While you find out how to unmute yourself, let's move over to another question in the comments, since we're short on time. This one says from Aloy, how on earth can you aim the neutrino beam so precisely at the far detector, which is 200+ kilometers away?
Yeah, that is a very good question. Do you want to answer?
I mean, I think we are quite good at doing these kind of things with laser calibration and so on. But maybe you have some.
Yeah, let's say that first of all, the neutrino beam is not so narrow. So essentially, when we're aiming a neutrino beam, it's actually quite open, the angle. So we don't have to actually like aim very precisely to a very precise angle. And actually in T2K, what we have is actually a cross that we monitor the neutrino flux, and we actually know where the center is. So I mean, the fact that we have off-axis, we are monitoring exactly where the neutrino beam is pointing out. And after that, we are actually creating a prediction of the neutrino field that we are expecting in the fault detector, given the data we have on the aiming that we have. But yeah, essentially, it's quite open. It's not like very narrow.
Thank you. I can see, Trivanpal, you are sharing yourself, so perhaps you can ask your question.
Thank you very much for your patience. Thank you very much for such clear presentations and all the incredible detector work done. I apologize that it won't be a question on all the work which you have done directly, but just to educate me a little bit. If I understood the main differences between the J-Park and Fermilab approaches is that of energy and the oscillation lengths. My naive question is that given a certain energy range, will the two approaches achieve similar sensitivities in terms of upper bounds, for example? Are they going to aim to give equivalent sensitivities?
Yeah, that's a good question. I think there are two different points here. The first thing is that T2K and HK are mostly aiming at the delta CP measurement. So they choose a relatively short baseline, not to be very sensitive to the matter effects, because the neutrinos don't travel for a long distance in the Earth, and the matter effects have little influence on the measurement that they make. While DUNE, on the other hand, is trying to do many things at the same time, trying to have a wide beam, to be under a wide baseline to be able to measure at the same time the matter effects and the CP violation effects that hopefully can be disentangled by the fact that these effects are different at different energies. So typically, if you were to do something similar to DUNE on a long baseline, with a narrow beam at rather high energy, then you will have some degeneracy between delta CP and the mass ordering. But the whole concept of DUNE is trying to have this wide energy beam to really look at the variations as a function of energy to try to disentangle the two effects. Then I think the main point is that Hyper-K is definitely going to make a statement sooner than DUNE on CP violation, in theory, given the current schedules, because it's more massive and it's really only, mostly measuring this effect. DUNE is trying to do many things at the same time, and ultimately, in theory, DUNE is supposed to have a slightly better precision on the precise value of delta CP, given the fact that it's really looking at two different oscillation maxima, and it's able to better make this measurement. But in the end, everything will come down to how well you can constrain your systematics in both cases that are very different, because we have very different targets, very different detectors. So all of this is theory for now. We will see in practice what happens.
Thank you.
Thank you very much. Now, in the interest of time, I wanted to ask Rachel, do we have time for one more question, or is it perhaps time to close the session?
We have time for one more. Yeah, definitely one more. We're going to squeeze everything we can out of the session, if that's okay with everybody.
Excellent. Well, then, if anybody has any more questions, make sure to raise your hand. But I'm going to ask the final one in the comments, which is, what about applications in machine learning in the data analysis?
This is a great question. That will be hard to summarize in 30 seconds. But yeah, the machine learning developments are really a central key to our reconstruction of the neutrino, because essentially neutrino, for the moment, when we are just looking at interaction of them, in the DUNE detector, we see many details. So we see the track with these electrons like showering. So to reconstruct just the energy of the lepton is already a challenge. And the machine learning method, like convolutional neural networks, are employed for the moment already, and being optimized to actually reconstruct as much as we can, as well as we can, the neutrino energy in the end. So this is really a central part of our reconstruction pipeline, let's say, softwares.
Yeah, it's really being heavily implemented. And I think maybe one challenge on the neutrino side is that we don't want our reconstruction method to be sensitive to the underlying nuclear model. And that's something that can be a bit challenging because we don't really know what's the underlying interaction model between neutrinos and nuclei. I mean, we know it partly, but not very well. And we really have to be very careful with all our machine learning models to be sure that we are not biasing them into assuming some underlying models, and we are really to go in depth in these details, but that's clearly something that is very well investigated in the field for now.
Thank you very much. Well, I would like to thank our speakers very much. It was a fantastic overview of the topic, and thank you all for being part of the discussion. For now, I will give it back to you, Rachel, to finish off this news from the labs event.
Thank you so much. So yes, I repeat what Adelina said. A huge thank you to you, Adrien and Pierre, for such a brilliant presentation. And thank you so much to you, Adelina, as well, for moderating the event so well. And thanks to everybody else who joined us. And we look forward to seeing you all soon. Thank you very much. And have a great evening. Thank you.